So in this problem, we're given a depletion mode N-channel MOSFET, and here we're given the gate to source voltage of this MOSFET as 1 volt, and we're also given a description of the various operating regions. So we've learned before that there's the cutoff region, triode region, and saturation region. And each of these regions have a different way of calculating the drain current given the relationship between the gate to source voltage and the pinch-off voltage, and in some cases, the gate to drain voltage and the pinch-off voltage. So let's see how we're going to tackle this problem. So usually I'll list out the givens in the problem, and that usually gives us a good roadmap of where to go. So what I've underlined first is this 1 volt, and the question says that this is our gate to source voltage. So that's basically saying that VGS equals 1 volt. And if we look at the bottom here, it also gives us our K and our VP. So VP is minus 4 volts. That's our pinch-off voltage. And there's actually another relationship that we find here. Because usually we're looking for VGD, our gate to drain voltage as well. Well, we have to look at the diagram here. And what we see is that D and G are connected to a common point by this wire. So what can we say here? Well, because they're connected to that common point, VG, our gate voltage, is equal to VD, our drain voltage. And knowing that, we can say that VGD, the gate to drain voltage, is just the difference of those two, and that's equal to 0. So knowing these three values now, we can make the conjecture that VGS is greater than VP, and that can be obviously seen here. 1 volt is clearly greater than negative 4 volts. And also, what do we know? We have VGD is greater than VP, because 0 volts is clearly also greater than negative 4 volts. And looking back to the relationships here of the operating regions, we have VGS is greater than VP, and VGD is greater than VP. So this fits the criteria of the operating region of the triode region. So I'll just write that down here, triode. And we also know K, so I'll just write that down here too. So K is 0.2 milliamps per volt squared. And then we can solve for ID because that's what this question is asking. What is the value of ID? So we'll plug that into the triode region equation. ID equals K times 2 times the difference of VGS and VP times VDS minus VDS squared. And so putting in the values that we know, we have 0.2 milliamps per volt squared as our K times 2, and the difference of VGS and VP is 1 volt minus 4 volts, and that's all multiplied by 1 volt minus 1 volt squared. And that gives us ID equals 1.8 milliamps after we do all the calculation. So that matches option C. So moving on, here we have problem 56, in which it states, in the full wave bridge rectifier circuit shown, if the DC load resistor RL is 10 ohms and the diodes are ideal, the average power in watts dissipated in the resistor is nearly what? So this question can be a little bit intimidating if you don't read it carefully. So it gives us an important piece of information here. This circuit is a full wave bridge rectifier with a load resistance 10. The diodes are ideal, so diodes are ideal, and it's asking us to find the average power dissipated. So to approach this problem, we have to know a formula for power. So we are given RL, and we're also given a voltage. So our voltage is 170 cosine squared, or 170 cosine omega t volts, and our load resistance is 10. So a formula that we know that relates voltage, resistance, and power is V squared over R. But since we're given a full wave rectifier, this is VRMS squared over R. And, well, what is VRMS for a full wave bridge rectifier? If you remember this, VRMS for a full wave bridge rectifier is the peak voltage Vmax over the square root of 2. And so we have here that our amplitude of this cosine wave of the voltage is 170. So we could plug that as our Vmax. So Vmax 170 over the square root of 2. And then that's our VRMS. So plugging that back into the power formula, P equals 170 over rad 2 squared over 10. And what does that give us? That gives us 1,445 watts. And that basically turns such an intimidating problem into something trivial just by knowing the relationship of a full wave bridge rectifier and the power given voltage and resistance. So that gives us option B.